Namaskar and welcome to episode number 7 of Understanding Feynman's Physics podcast. We have 7 episodes of electromagnetic waves and trying to understand the 4 laws, and those laws depend. The way you imagine those laws is through some way of having a mental model of what are these waves and what are these forces, and how do charges affect each other over a distance, and there must these electric field lines, and the charges, and the force of the electric field vector and the magnetic field vector. What's going on? What is actually going on? What is the real truth? What is the actual truth? A lot of so this is a question which happened quite long ago, when people were considering how exactly can magnets work over a distance, when everything we do requires touching and pushing. Every force we apply is through direct contact. How can magnets work without any direct contact? Well, what it turns out, when you try to explain the direct contact and you go into the molecular side of it, you realize that the direct contact itself is only electromagnetic. At that level of the molecules, nothing is actually touching. It is electromagnetic. So how can you even say that using the actual touching force is the only way you can apply the force from one object to the other, when the very act of doing it is in favor of electromagnetism? So that's the kind of question Richard Feynman really puts forward and makes us understand that this is not the way the actual reality is. The actual reality is not made of fields and charges as much as it is made of the actual vectors and the value of the electric field. The question is not what is real, but what is convenient. What is convenient to us, to our way of looking at things, to our ways of what makes us make sense more. Well, you might say the field lines make a lot of sense, because the field lines shows where the charges where the force would go on the charge which is in that field, in that electromagnetic field, right? But one of the biggest problems with field lines is that two sets of field lines, one from the first set of charges and the other one from the other set of charges, it's hard to imagine how they would superimpose through field lines. What is the resulting field line? And what happens is, you realize that superposition is the most deepest and basic principle of electromagnetism. It's without that there is no, how do you even add the charges of the first group, so field lines are not even good at trying to understand superposition. um, Charges are fine. Thinking about forces between charges is a good way to do it, only if the charges are at rest, related to you, in relation to you, charges are at rest. At that time, it is easy. But if the charges are moving, it's a big problem. The equation that turns out from that behavior through this model of charges and the forces is so complex. It's like the three body problem in gravitation. Gravity, three bodies. Maybe that I don't really understand it properly, but that's the idea. So what is remaining? What is remained? What remains with us when we um, mathematical way is the last way to do it, and it's straightforward, but it's so abstract, and it's an unfortunate thing that it's abstract. It's abstract um, but it's the most once you get comfortable with it, Feynman says that it will make the most sense. And it's like getting comfortable with artificial meat or something, like it's you just need a little bit of a hurdle to, I don't know, I don't think I've really got over that hurdle. But the way to look at it mathematically is to see that there is a vector in every position. There is some force that lies this there is this mathematical vector in every place, in every position. So what do we get? What do we get when we see it in a mathematical way? Well, I have yet to go through that part of this field, but he touches upon this idea that magnetic effect is a relativistic effect of electric charge, electric field. In this sense, I didn't really get it, but this is the idea that if one observer who is at rest, so let's say if two charges are moving through space, they will exert a magnetic force on each other. We all know that. We all already discussed that. Charge creates an electric field, and an electric field converts to magnetic field, and then the moving charge in an electric field creates a force, right? So if that is happening, you can, as an observer, can either see that phenomenon while it's at rest compared to them when they're moving across, and then you'll notice the magnetic field. But if you're moving with the charges, you should not feel that magnetic field. You should not, because to you there is no motion. So, but the force between the two particles shouldn't change according to your point of view. You are not a part of the system. So in a way, he says that you can think of it as that, but he explains it very precisely, which also brings us to the actual equations, because you have to actually look at the equations now to understand how that is happening. And I haven't looked at the equations yet, but there's a very interesting part to it. Even if the velocity, because even in our wires in the homes, the electricity in our homes, when the electrons are moving through the wire, they are going at a distance of 1 centimeter per second. That's not relativistic speeds. You don't think of relativistic speeds as that. You think of, okay, relativity says that if someone is moving at 99% the speed of light, their length is shortened by 10 meters or something, or 10% or whatever. It's at that scale. It's even at the scale of few centimeters per second. And why is that? Because even at that small level, even at that level, the number he says is, it's the strength of the resulting correction because of relativity is of the order of 10 to the power minus 25 of the charge, the force of the charge. But the strength of the electric field. But the point is, the electric field is totally balanced out because it's of the same protons and electrons. Even this small 10 to the power minus 25 force is very strong, and it looks like that. It can actually overcome Earth's gravity. If you point a simple magnet to a nail, it will pick up the nail. And this is what I understand. I'll go through it more, go through the equations more, and then there are some other things on the history of the discovery of electromagnetism. How do they even start? The first moment of discovery, where someone looks at a magnetic stone, and the first time someone looks at static electricity, and all those things, and that will happen tomorrow. Thanks for listening.